Stability and rigidity defects in wood products are estimated to cost the forestry sector tens of millions of dollars a year. Researchers at forestry CRI Scion are using new technology to find out what's going on inside the trees and what that means for New Zealand's wood processing industries.
The research is a fundamental part of a 6-year program that is co-funded by both industry and by government. And the key issue that we're trying to address in this part of the program is what are the important factors that impact on wood stiffness and stability. We've got two pieces of 4x2 here. This piece here is what I'd call fit for purpose. It's straight, stiff, and the one on the left here, you can see it's got a fair amount of bow, and it's certainly not appropriate for any end-use application here in New Zealand. From a forest grower's perspective, what we're interested in is trying to understand how we can manipulate our stands through genetics, through management, and through putting the right species on the right site, actually producing timber that's fit for purpose. So there's minimal downgrade, and our processors are actually getting maximum returns from processing that wood. The information gathered from this work will be used primarily by forest growers. The idea is that by sampling several thousand of these trees, we will actually be able to develop some relationships between genetics, site and management, and what ultimately comes out the other end in terms of wood products. We're at the point now where the Scion scientists have actually been able to reduce the cost of acquiring this important material and data, taking it from about $10,000 a tree down to around $1,000 a tree. And that's a very important element in terms of being able to actually do an appropriate level of surveying to get the sort of information that we need.
The idea for us was to get a better answer as to what the quality of that stem would be, and the only way to do that would be to look at the whole stem. So we've been developing methods here where we can dice up a stem into very, very small parts to 3-centimetre biscuits, basically. The process we're going through at the moment is basically to take a tree from the forest, take it into a pole mill. They are cutting these up for us into 3.5-centimetre segments. Then the cut face is photographed so that we can get a record of every surface. We can then stitch those back together and give us a look at basically the inside of that log, so we can pick up any defects that can be seen visually. The non-visual things we then sample every metre, and we pull a disc out of the sample and we bring that back here. Once it's back here, we'll run it through a surfacing so that we can see that surface a lot better. We then photograph those again, so we've got another record of the discs that we're actually interested in. Following that, we look at the green disc and put it through a flatbed scanner, which we've modified to be able to basically follow light through the piece of wood, which indicates the grain angle over the whole disc. So we're seeing the straight lines from the mask coming through, and we see the variation coming through the disc itself, so we've got more of a curve into those lines, and that's the spiral grain. Once been through that part of the process, we'll dry the disc, and then we're currently sending them to GNS to put through basically a carcass X-ray, where we can determine the wood density across that disc surface, and then we're sending it to the University of Canterbury, where they will look at ultrasonic velocity, which will give us an indication of the stiffness profiles within that disc. What's next is to bring all these tools into an even more efficient way and to scale up to be able to do larger trees. We have a project which we're hoping to finish by mid-next year, is to build a robot which will bring in the USV, the X-ray, the NIRs, and the spiral grain measurements all into one machine, and hopefully then we can go through a high throughput data capture system.
This program was made with funding from New Zealand On Air.